We're looking at linear transformations and particularly what happens with bases or dimensions here. So if T is a linear transformation from V to W and beta is a basis for V, then R of T equals the span of T beta. In other words, what's T beta? Well, you take the elements of beta, and so T of V1, that's an element of the codomain, right? Out to T of Vn, and those span R of T. So you want to think about R of T, just think about what those things are doing. Okay, so how does that proof work? Well, if you have set equality, you have to have containment both directions. Probably the easier direction is to pick something in the span. So let y be in the span of T beta. Okay, what's that mean? You can choose A1 to AN. Some of them could be 0 in F, such that y equals A1 T of V1 out to AN T of Vn, right? So that's what it means to be in the span. This is what I have. This is what it means. What do I want? I'd really like to say that y is in the range of T. Well, what does it mean to be in the range of T? It means there's some element that maps to it, but I have y is equal to that. So think about it. What do you do with linear transformations that look like that? You say, well, that means y equals, by linearity, you can add the terms. By scaling, you can put the constants in, really scaling, then linearity. A1, V1, out to AN, Vn. That's the very definition of being in the range, is it's the image of a particular element. Okay, well, what about the other direction? You can imagine how this goes. We're going to pick an element that lives in the range. What's that mean? That means you can choose an element in the domain such that T of x equals y. That's what I have, that's what I want. Sorry, that's what I have, that's what it means. What do I want? I want to be able to write this as, let me do this. I need to show y equals A1 T of V1 out to AN T of Vn. In other words, I need to be able to write y as an element of the span. So how could I do that for some AIs in the field? Okay, so how can I do that? Well, what could I do? I don't know how to do it with y, but I do know how to do it with x. So since beta is a basis of or for V, choose A1 to AN in F such that x equals A1 V1 out to AN Vn, right? That's what you do with bases. And now I don't have V written this way yet, but I have x written this way. But you can sort of guess how we're going to deal with that. It's a linear transformation. So T of x, y is T of x is A1 V1 out to AN Vn. And now because it's a linear transformation, I can break it apart. That's exactly what I need. That's obviously an element of the span of T of beta, right? Okay, so that's a helpful element of this upcoming proof. which is a named theorem. But first, I need two definitions, okay? We have the null space, but the dimension of the null space, is called the nullity. So the nullity is a number. The null space is a subspace. And we have the range, that's a subspace of the codomain, and the rank is the dimension of that. So the nullity is the dimension of the null space, rank is dimension of the range. And the dimension theorem says if you have a linear transformation T from V to W, and if the dimension of V is finite, then the nullity, that's a number, plus the rank equals the dimension of the domain. Now that's a little surprising because the domain, this is the dimension of the domain. This is the null space, which is the dimension of the null space, but this isn't in the domain. So maybe that should be a little surprising to you, but it's a really powerful theorem. And the proof uses a nice technique that I think is worth thinking about. Suppose the dimension of V equals n, and the nullity of nullity T, I guess is how we're saying it, nullity T equals K. And of course, K has to be less than or equal to n because the null space is a subspace. We're going to choose a basis. V1 to Vk of the subspace for nt, and extend to V1, Vk, Vk plus 1 out to Vn, a basis for V. So we have a basis, and we know these elements are the null space, which is a subspace. This is a basis for V. That's the technique we'll see other places, okay? So if this is n and this is k, it is enough to show that theta equal to T of Vk plus 1 out to T of Vn is a basis for the range of T. Because if that was true, that's the difference, and that's what the rank is, right? So I need to show that these elements are actually a basis. So a basis, right, it has to span, and it has to be linearly independent. So let's think about R of T, the range. Well, you can write any element of the range as T of any element of the domain. But how do you write an element of the domain? The domain is A1, V1, can be written as A1, V1 out to AK, VK, out to AK plus 1, Vk plus 1, out to, better have a little more room, a n Vn, such that the A1 to AN are in the field, right? Why? Well, because you can write any element of the domain like that, so that's really the range. Now, you can guess what I'm going to do here because I have a linear transformation with a sum inside. I'm going to break it apart, so I'm going to have A1 T of V1 out to AK T of Vk plus AK plus 1 T of Vk plus 1 AN T of Vn. Still coefficients for any coefficients in F. Now, why would I highlight these? Well, because by choice, T of V1, that's in the null space all the way out through this. So this is 0 plus 0 plus 0 plus AK plus 1 T of Vk out to an t of Vn. And I suppose I could stop that subscript at k plus 1 if I wanted to. But what have I gotten? I've got the range is actually equal to, well, what is that? That is the definition of theta, right? That is the span of this set theta, right? So span of theta, right? Okay, so I've showed that this set theta spans the range. Now I need to show that theta is linearly independent, right? How do you do that? Well, you choose BIs in the field such that that linear combination equals 0. Just for variety's sake, how about I show you some notation here? So you can do it like this. I could do it with the dots like I was before, but probably good to see both methods. Let's choose that equal to 0. Well, what does that mean? That means t of, pulling the linear transformation outside, t of the sum I equals k plus 1 to n of bi vi equals 0. So that means it's in the null space of T, right? This maps to 0, it's in the null space. So what can you do? You can choose CIs in F such that if this is in the null space, I ought to be able to pick CIs so that I equals k plus 1 to n of bi vi equals some linear combination of the things that's the basis of the null space. So Ci vi, but here I'm just sending from I from 1 to k. Okay? Now, what do you have there? Think about this. You have entirely different VIs. Thus, what does 0 equal? 0 equals I equals 1 to k Ci vi minus I equals k plus 1 to n bi vi. Oh, I have a linear combination of a basis of v that's equal to 0. So since the VIs form a basis of V, all CI and BI equals 0. Therefore, theta is linearly independent. And we have the basis, the theorem.